Good evening. Welcome to my presentation regarding algebraic topology and optimal transportation, our program for building spines from Singularity. The fundamental definition of algebraic topology is Poincaré's definition of fundamental group, universal covering spaces, and orbit quotients. Meaning, we study a group to be the symmetry group of some universal covering space. Our goal in this thesis is to construct such covering spaces for duality groups, and our goal will be to build the space as small as possible, as compressed as possible. We have a technique for explicit constructions of small dimensional classifying spaces, applying to groups gamma, which are infinite discrete duality groups, not Poincaré duality groups, but higher rank Algebraic duality groups. Many examples: Z, Z2, Z3, Z4, blah blah blah. Arithmetic groups of Q-reductive groups, this is where we actually started. SPZ4, SPZ6 is interesting. Mapping class groups also applies. Knot groups, that one's easier. I'd ask Dror if he knows any other higher groups, etc. We presume that a user already has an initial explicit geometric E-gamma model X at hand. Some finite dimensional Cartan-Hadamard space with computable group action, isometric, proper discontinuous, free, and such that the quotient has finite value with respect to the Hausdorff volume of the metric. All models not created equal. We prefer Teichmuller space with Weil-Petersen geometry. For arithmetic groups, they act on suitable spaces of quadratic or Hermitian forms. And actually, I learned that Harish-Chandra has a theorem, Harish-Chandra canonical realization theorem. Very useful. That's the best model we found. GLZ2, it's a basic example, acts isometrically on the hyperbolic disk. There's many actions, actually. We have our own favorite in terms of quadratic forms. Voronoi model. Typically, if X is a geometric E-gamma model, then the space dimension is much larger than the cohomological dimension. When the group acts with finite measure on the dimension, then Berry-Ekman have an important formula for precisely computing the cohomological dimension. It is the space dimension subtract some rank. And we'll see what this is. This is a duality formula, where Q is the spherical dimension of the dualizing module. We'll say more later. Our thesis constructs, and we mean explicitly, challenge me on that, gamma invariant closed subset Z of X, where dimension is, at least generally, it's approximately cohomological dimension. And always for which the inclusions are continuous homotopy isomorphisms. Moreover, we construct explicit gamma equivariant continuous deformation retracts of the space X onto Z. We also describe a technique, and that's our main aim here today, for achieving Z with max codimension and obtaining equality. These minimal Zs with equality are called minimal spines. I'll say something that already what we're going to do is study an orbit, and step one is to see in this geometric model that the orbit does not uniformly fill the boundary. It avoids dark zones. When we identify those dark zones, we then cut them out, excise them. We obtain a nice boundary, and we're going to then consider -1 charges distributed along the boundary and -1 charges distributed along the source, and -1 charges with Coulomb forces. we take a totally elementary point of view here. Then there's a certain energy minimizing configuration, and the singularity structure will be the spine. Now, some people might say that's all obvious for the hyperbolic disk, rank 1, very simple. But our point here is that everything we just said works verbatim for every group. There's many ways to describe the spine for the disk. There's one way that generalizes verbatim to all examples. Now, spines and souls have a fun tradition in geometric homology. Klein, Minkowski, and reduction theory, Poincaré, as we just saw, Steenrod problem, constructing homology. Tom studied Steenrod problem, found a way using transversality to represent fibers. We could cycles. We could represent that further. Lefschetz, we have intersection duality. Thurston, we have more ideas about the structures at infinity. Gromald, Chigre, Perelman, Soulayash, McConnell, they started building spines based on the infinity, data at infinity. They're all beautiful answers to a very old question of how to construct new models of old spaces and to be as explicit as possible. Textbook constructions of E-gamma models are typically abstract, external, dislocated. They require perfect knowledge of the group, like a presentation, generators and relations. That's impossible in practice, especially for mysterious groups, like arithmetic groups. Milnerized construction, Wall, Postnikov towers, Cayley graph strips complex, they're all interesting, but I'm too stupid to use them. We only presume limited knowledge of gamma. This limited knowledge is very useful, though. It's this geometric E-gamma model X, which already, solves, say, the word problem, since you just study whether a point is moved or not moved. And what we do from an initial model is develop a program for in situ reduction to a spine. We don't build external spaces that live out in Never Never Land. We exactly tell you how to reduce the given model. We say the given model already has all the information needed, and we compress that model based on that information. So we construct the spines as explicit subsets of initial model X. Actually, I'm grateful to Dror's course about Mathematica, Wolfram language. All this was ready-made to be implemented on Wolfram. You have to change your attitude. Spines are not hidden. Spines are readily displayed in the locus of discontinuity of deformation retracts. Now that's the idea. The technical definition, what's really developed in our thesis, is that spines are readily displayed in Kantorovic's contravariant singularity functor of C-optimal semicouplings. Say more later. Well, many terms to define. Creating a relation between measure theory and topology, we have to set up some definitions, ideas. For us, this first starts with source and target, with the excision models. Then the excision model has interesting homology at infinity. Steinberg modules, we get Steinberg symbols and filling. Then we start translating them and build up chain sums, and we ask for well-separated gates structure. And that's just for mass transport. We have to have costs. I need to introduce repulsion, gated repulsion costs, optimal semicoupling, concave potentials, C-sub differentials. It's all beautiful theory. But everything is summarized in Kantorovic's contravariant singularity functor. Boltzmann has P log P, N log N. Just give me this one. Now, singularity is an overburdened term. I like our definition. I say singularity arises wherever there is competition for limited common resources. It's about ripping things in two. I'd say it's also why countries share borders. There's competition for limited resources. Countries don't just curl up away from each other. They go face to face, head to head. I'd even argue that there's an economic proof of four-color mapping theorem. Never mind. Here's a basic example. You have 2 points, y0, y1. They're both thirsty. They ask for some energy from the background. If they're far enough, they have no competition for space, so there's no singularity. Boom, boom, they just fill up. Now, if they get a little closer, then they begin competing, and singularity appears. What's interesting is if you think about changing the mass of y0, y1 a little, the singularity is very stable. Actually, the equation is totally stable. We'll say more. Here's another example. You have 4 points, A, B, C, D. They're thirsty. They ask for some energy from the background field. Boom, fill up. But they have some competition. They rise up and meet each other. And this ripping locus has some more, just a little structure. This is what the functor describes, this data. And find criteria for the homotopy series. So C, well, let's grab it. Now, here's the point. The singularity functor is explicit. I said I'm constructing things, and I mean it. The reason we can construct them is because we're studying measures. We can build measures just as point configurations on Wolfram. We can sample them. We can find the optimal transports for the given source target measures. But there's some key definitions. C concave potentials, C subdifferentials. Beautiful story. But the point here is Kantorovich duality. You might ask, how does topology come out of measure? Well, you ask for, it's all about cost. You ask for the minimal transport measure, semi-coupling from source to target. You look for the one that has minimal cost. In terms of cost, there's always a dual theory in terms of prices, shorting and selling prices, puts and sells. In terms of a transporter for a very special class of C concave potentials. The max is equal to the min, actually, beautiful fact. And it says the support of an optimal semi-coupling is very special. It's supported on the graph of the subdifferential of the C concave function. Now you get some interesting inequalities here, and this is how we're going to get equations. C concavity means there's the C transform. I could define it. And what's interesting is when equality is characterized, it's if and only if there's membership. And here's the way to say it. It's if and only if y belongs to the argmax of this y parameter family of functions. You have a y parameter family of functions. You're at a given point. You look at this family. You look at where maximum is attained in terms of y. That's where you go. The max value is by definition the C transform of psi. Now, again, when you have a C concave potential, it means that the singularity consists of X, for which this argmax set, Y parameter family of functions, for which X, for which this Y parameter family of functions contains Y. Just give a little abbreviation, two-pointed cross difference. This implies a set of equations. It's a set where these differences are equal to 0. Turns out. And actually there's symmetry in terms of phi, y0, y1. Actually reduces to this many equations. Now our theorems, we want topology of these singularities, and there's a basic implicit function theorem. And it requires the gradients be sufficiently linearly independent. So it's important, especially when they're non-zero. Now these cross differences, it's a very interesting function. Find, for quadratic cost, we find it's basically linear in X. All fibers connected and critical point free. For our repulsion and gated repulsion costs, cross difference, yeah, it's real valued, but so beautiful, it has poles. It goes to plus infinity, minus infinity at the two endpoints, x, y1, y0. Next, what's very important is all fibers are connected and critical point free. They give very nice foliation of the space. Now here's our applications. Contravariance says that the cells, ZYs, are local cells in X, and they are parameterized contravariantly by subsets of the boundary. Contravariance means you have a certain inclusion relation and lots of morphisms, inclusions between all the cells. We find local criteria which ensures that these inclusions are homotopy isomorphisms, and we can construct explicit continuous deformation retracts using the variational definition of the C subdifferential, those equalities and inequalities. These local reductions, using the contravariance, they assemble into global reduction. So here we have another global theorem. Basic consequence of functoriality. We identify an index J such that the local cells and their local homotopy reductions assemble into a global continuous reduction. So we find some index J such that all those arrows are homotopy isomorphisms. And all the way we construct explicit deformation retracts, and the dimension of these subvarieties, they're all codimension J. It's fun, the definition of these retracts. It's a gradient flow towards poles using the cross difference functions. Very amusing. Applications need index to be as large as possible. Best results obtained with our anti-quadratic gated repulsion clauses. We'll elaborate. Here's an example of a pair of pants. We get the theta singularity. So we see the pink, that's the activated domain for the repulsion cost. We've excised some horospheres. Here we got some circles. And we find this theta graph. Local half-space conditions fail at these x's, so we know we can't retract any further. Now again, the application is to build spines. So like we said, we have to start with some initial model, and then we do an excision, gamma rational excision. That's how we obtain the proper discontinuous boundary with the well-defined radon measure. Excision is obtained by scooping out this family of gamma rational horribles. Very general. The key property is that the boundary is the homotopy type of some wedge of Q spheres, countable wedge. So there's countably infinite constellation of spheres at infinity, and the group gamma acts like permutations on them. It has a very good action. It's very transitive on these spheres in principle. Now, the excision is contractible along the exact sequence in relative homology and the gist of geometry assumption implies that you get an isomorphism between these two two homology groups, and there's a canonical flat filling for every sphere. Every sphere gets canonically filled, flat filled, to a disk, relative cycle disk. These filled relative cycles have an important role in terms of intersection homology, say Poincaré-Lefschetz duality. And Beery-Ekman interprets these relative cycles, identifies them as dual, actually, to the minimal spine's fundamental class. So in other words, dimension of this filling is the max codimension of the minimal spine. That's why we have that formula, codimension Q plus 1. It's this Q plus 1 for the relative cycle. Now, it's easy to observe that this filling, it's a disk, deformation retracts to a point. Everybody knows this. And you get an idea. You ask yourself, how do I continuously interpolate and extend these local retractions? Extend them to a reduction of the whole space, the global space, onto some spine, minimal spine of exact codimension. Now, we argue a new solution to this interpolation problem. We say it's achieved with the gated repulsion cost and the Kantorovich functor on the appropriate excision. So, here's how it goes. You start with some initial geometric model. You take an orbit, you see what happens. The orbit avoids these dark zones and you excise them, remove them, to obtain a boundary. Then you start looking at relative homology of the boundary. Take translates of this relative cycle by the group. And this is a solution to a problem we call closing Steinberg, we'll describe next. then at least you know that dual, in terms of dual, the spine has to be transverse and intersect to each of these disks at a point. But you get the problem. How are you going to interpolate? This word choice of cost is very important. Singularity depends on the costs. Actually, all the geometry of the measure is induced by the cost. Now, habit suggests choosing quadratic distance, but best results obtained with our anti-quadratic costs, repulsion, negated repulsion costs, c tau, c zeta. So quadratic is the worst cost. So here's basically our program. You want to achieve equality? 1. You have to replace space initial model with appropriate excision. Find the dualizing module. Then we're going to do something with this dualizing module called close the Steinberg symbol. That will allow us to construct a gated repulsion cost. That gated repulsion cost will be able to solve the interpolation problem and homotopy reduce sufficiently deep into the singularities of an optimal coupling and obtain our deformation retracts with the exact right dimension. Let's introduce the repulsion cost. Basically, like I said, it's like an electrostatic force. You have some activated electrons, y0, y1, blah, 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 minus charges at these, in this case, extreme points, but you could say boundary. And then you ask the net force on x. You basically compute that net potential on x. And now that's sort of uniform with respect to the boundary, but then you choose a y0 target point, and there'll be a discount if you want to have transport there. Otherwise, without this term, it's independent of y0, just at high average potential, but you have no preference to go anywhere else. One-dimensional cost. Now, I should draw you some pictures here. This is interesting. Study these formulas. We'll illustrate them. See, we get a difference of quadratics, one-dimensional quadratics, two poles. So let's consider a closed unit interval with boundary at 0, 1. Source is some uniform distribution of -1 charges. We say 15 charges if you count them. 1, 2, 3, 15. We said the target is a distribution of 4 -1 charges. Well, here it doesn't take much. The cost will start from some minimum, these 2 points, and will transport to -1. These two will transport to this other end, and there's no competition between them. There's no singularity. However, if you increase the target mass, then you force more electrons to be activated, then you force some competition, make resources more scarce. Here we have 15 charges go to 6 charges. 1, 2, 3, 1, 2, 3. They're going to start competing here at the interface. Boom. Now we have a singularity. And it's interesting to tweak these numbers a little. 15, 16, make them 14, 7, make them 13, 5, blah, blah, blah. The singularity, it will move, the domain will move, but even the singularity will move, but the geometry will stay the same because it's basically the same equations describing it, as we'll describe. Let me compare it now. Like I say, it's anti-quadratic, so let's compare the picture with plus charges, minus charges. I say that story, plus charges to minus charges, that's your quadratic cost. You have +6 charges. You want to activate with minimal energy some equal number of mass, say, -6 electrons. But, well, they stay far apart. They fill from the minimum. The minimum is at the boundary. Now, constructing the gated repulsion costs, we have to introduce this problem called closing Steinberg. Totally idiotic elementary problem. Low dimensions, it's basically the problem of how do you stitch a football from a collection of panels. Actually, if you look, the platonic solids are all solutions of closing Steinberg, where panels are a triangle, a square, a pentagon. They're just ways of closing the shape with the squares, and in a convex form. Now the panels in our applications are these flat-filled Steinberg symbols, the disks, the relative cycles, that were filling the spheres at infinity. we're looking at their translates through space. Now, in general, the translates are going to totally displace them. We want translates which have large overlap. We want some correlation. So here's the formal definition. We want the panels to translate and assemble a closed football. That means we want the chain sum overall to be non-trivial. We want the chain sum to have vanishing boundary. That means the ball gets totally stitched up and it's closed. We ask for some convexity. We don't want this ball to be some freak ball. It should be able to roll along the grass. And this is most important. We have a very restricted kind of gate structure we want. Any kind of football will have translates and there'll be some overlap, but we want this overlap, these gates, to be precisely the panels, precisely the Steinberg symbols. Now, just to convince you it's not trivial, the first two are just homological conditions. Actually, if you write them out, what they mean in terms of chain groups, it's syzygy in the projective resolution of D. I've never seen anyone study that. There's a paper by Cremona that's interesting. Manin relation. Fourth part, the well-separated gates, it implies that the translates define a chain sum, and the action of the group on the chain sum acts as a shift operator. It's an action equivalent to gamma cross gamma. Shift. But we want intersections, because we want the union to be connected. Here's an elementary example of what I mean by taking some translates and making sure they close. Here you have these basic cells, they're translating around. And that's what you imagine X. You're just a point, that's the source, living inside. But at every point, you have well-defined coordinates with respect to the boundary of the chain sum. Now, the gates terminology. The idea is, as you're moving, point X occupies some end, but we want to think of variations. It moves and changes and crosses into other ends. We're not trying to make a fundamental domain or nothing. But if it's going to switch ends, it has to pass through a gate. Now, we look at coordinates, lambda x, if it's in a F, we look at its coordinates relative to all the gates. Lambda x, important measure, it's actually the most computational intensive part of our implementing in a Wolfram. It's challenging to have good coordinates for it. But it has nothing to do with our construction, it's just a general problem of finding these max entropy barycentric coordinates. Basically, how do you apply Krein-Milman on Mathematica? Make some notation. We're interested in the geometric mean of the restrictions. So for example, if a point X is interior here, then in terms of its barycenter measure, say it has no mass with respect to y4 or any of these points, and its geometric mean is therefore 0 along these gates. Only the incident gates have non-trivial mean, geometric mean. If X lives on a gate, then that's the only gate that has non-trivial geometric mean, meaning non-zero. Then for every gate, we have our earlier repulsion costs, and we're going to define the gated repulsion cost as a weighted sum per the gates supporting X of these geometric means. This C zeta is a continuous assembly of the basic continuous repulsion costs. It's continuous. And when X belongs to a gate, then it reduces to just a rescaled factor of the gated repulsion. It has its own singularity functor, and our proposal is finally that enough half-space conditions are satisfied all the way up to index J, and the corresponding singularity can be equivariantly homotopy reduced to a minimal spine. So what we mean, you're in a chain sum, and so now X doesn't just see one gate, it actually sees a few because it's contained in the convex sum. These gates might actually share some vertices in common. It's fine. So we're going to look at repulsion cost with respect to all gates. It has an average energy reweighted by the geometric means. And then if he wants to transport to a point y naught, say it's this point, well, for this gate sum he'll have a discount, but all the others, they'll have nothing to do with it unless they share some vertices in common, which is possible. You don't see it here. Then the idea is, here's how you're going to see the singularity be interpolated. Because the cost restricts to the basic cellular cost here, and there's no critical points, I'd have to convince you of that in a proof that there's no critical points. The fibers never sort of split or decay. They're always connected and they interpolate. And that's how we solve the interpolation problem. That's how we propose spines be built. Let's show you the movie again. Took an initial space model to find the excision. Start studying the relative cycles, Steinberg symbols. Close the Steinberg symbol, find some translates that give you a well-defined convex set F, such that translates of F now give you coordinates all over the space. It's a basic partition of unity. With respect to the gated repulsion cost, study the optimal transport, look at the active domain, that mass that's activated. Something important here about the ratio. Source transport has to be sufficiently competitive. But anyway, then you'll get your singularity structures. That'll be the spine. Thank you.